Hello, welcome to Maths with EJD. In this video, we'll continue to look at SciPy module by module. And here, the module we'll be looking at is the one on linear algebra. Okay, so as we know already, as we saw from the introduction, we know that everything related to linear algebra is done with this linear algebra module in SciPy. So that takes us to the 15th video in the scientific computing with Python playlist. All right. So we have this, the SciPy.LinAlg module, linear algebra module. Of course, like you know already, check the description box to get a link to the notes for this class and all the previous notes, all the previous videos actually, so that you can, if you choose to follow as I do it, I think that'll be a very excellent way of learning. Okay, then of course, if you have not subscribed, be sure to do that. Hit the notification bell also, so you can always get alerted when a new video is released. So let's go to what we have, the SciPy.LinAlg module. The SciPy.LinAlg module, like we already know, is part of the SciPy library, and it provides a comprehensive suite of linear algebra functions that are essential for numerical computing. In this video, we will explore some of the key functionalities of the SciPy.LinAlg module, along with relevant examples. First of all, since we are dealing with linear algebra, it means that we can solve systems of linear equations using LinAlg. So that's what we're considering. First of all, solving linear systems. And of course, in the LinAlg module, we have to, so what we need for that is the solve function, solve. So SciPy is the library, LinAlg is the module, and solve is the function. So you have SciPy.LinAlg.solve. So the key thing here is that solve. For instance, you want to solve AX equals B, where A is a matrix and B is a vector, just like what you have when you're solving system of linear equations, like the one you have here. You want to solve for x, y, and z, where you have 3x plus y minus z equals 4, x plus y plus z equals 10, x plus 2y plus 2z equals 18. If you look at the matrices playlist, we have different methods with which we can solve this. Of course, here you can actually use the elimination method and things like that. But here we are computing. So how do you translate this into computing? So from that system, right, since the whole idea of computing boils down to arrays, so you have to represent the system as a matrix. And of course, so the A here is actually the coefficient of the variables, coefficients of x, y, and z. So, and that's why, okay, let me put on the line number so I can easily reference the lines. Okay, so of course, lines 1 and 2, you import numpy as np because we need numerical Python, because just like we saw in the first video on SciPy, that SciPy is built on numpy, and numpy's functionality is about arrays. And since you need arrays to declare systems like this, you need to, so you need numpy too. So you have to import numpy as np, and then from SciPy.LinAlg, you import the solve function. All right. So line 4 is where you declare the coefficient of the variables. All right. So A is np.array, and then you need it to be a 3x3 matrix. In fact, let me print that so you can see what it looks like. So I print that, and then let's say we need a blank print to give some space, and then we can also print B so you can see what it looks like. Like you see from the introduction, A is a matrix and B is a vector. That's like a column matrix. So I can put a blank print here too. So in line, okay, here we're printing A. So in line 4, you have the coefficient of the variables. That's 3, 1, 3, 1 minus 1. That's what you have in the first list. So we are making a numpy array from a list of the coefficients so that we can have a 3 by 3 matrix, a 3 by 3 array. So you have 3, 1, minus 1, and then you have 1, 1, 1, and then 1, 2, 2. And of course, so this print is going to make you see what that looks like. And then for B now, you're printing the vector, the column vector that is, you want to print that. And then, so where the solve is coming in here is line 14. So you now say X, that is the solution to the problem, right? So line X, you now solve A, comma B. So you have the matrix and the vector. So you can now print the solution X, which is this X now. So if I run it, you see all of that. Okay, it takes a bit of time, and then you see the solution. So you can see A is actually this 3, 1, minus 1, 1, 1, 1, and all that. And then your B is this 4, 10, 18, like that. And then the solution, when you solve, is 2, 3, and 5. So it's actually a fast way. So probably, one thing I do most times, maybe when I'm teaching online tutorials and I just make up a question, I can easily use this to check what the solution is, so that when I'm actually really solving it with the students, I already know what the answer is. So that gives me a bit of confidence, and it eliminates all the possibilities of mistakes, right? So that is how to solve system of linear equations. So all you just need to do is declare the array, declare the coefficients of the variables, and then declare the vector, and then just solve the matrix and then the vector, like that, and then you just get your answer spewed out, 2, 3, and 5. So that means X is 2, Y is 3, and Z is 5, basically. So that's so cool. So you can then go ahead to have maybe a 2 by 2 matrix, 4 by 4 matrix, any kind of matrix you need to solve like that. Okay, so let's talk about computing determinants and norms. Of course, determinant is more like the magnitude of a matrix, and it's closely linked to the idea of norm too, So in this case, if you are looking for determinant, you need the det mode, the det function. If you are looking for norm, you need the norm module, the norm function rather. So you have the SciPy library, LinAlg module, and det and norm functions inside LinAlg. Okay, so of course that would mean, if you want, the example is to find the determinant or norm of a matrix, or better still, determinant and norm of a matrix. Okay, so the same matrix we worked on before, we now want to find the determinant of this matrix, and okay, I want to find the determinant and the norm of that matrix, like that. Okay, so again, what we just need to do is okay, fine, you have extracted the coefficients of the matrix, right? So this matrix A now is actually the coefficients of the variables you had up there. So you just declare that, just like what we had before. And then, so for matrix norm, you just say norm A. For determinant, you just say norm, you just say determinant A. All right, and then you can print each of them. So in line 9, you're printing the matrix norm, and then in line 11, you're printing the determinant. Of course, if you don't know how to calculate the determinant, you can refer to the matrix playlist. So if you run this, you just get the answer. So the norm is 4.79, blah, blah, and then the matrix is -2. And of course, if you check the matrix playlist, you discover that for a matrix to be non-singular, that is, the matrix the matrix has an inverse. It means the determinant is not 0. So here, the determinant of this matrix is -2. That means the determinant of matrix A is -2. That means that you can find the inverse of that matrix. But if the determinant were to be 0, then of course you won't be able to find the inverse. And if you cannot find the inverse of a matrix, then you say it is singular. If it is not singular, then you can find the determinant. Then you can find the determinant and then the inverse. So no determinant, no inverse, basically. All right. So let's go to eigenvalues and eigenvectors. Of course, these have some implications in real life, right? Like even in data analysis and all the eigenvalues and eigenvectors, they have their meanings. Or when you talk about structural dynamics, solid dynamics, right? when you talk about vibrations and things like that, eigenvalues and eigenvectors have a role to play in all of that. And the function you use here is the EIG function in the LinAlg module, of course, in the SciPy library. So example is calculating the eigenvalues and the right eigenvectors of a square matrix. So again, the same matrix, I say find the eigenvalues and eigenvectors of the matrix. So the job is to translate the matrix into this array you have in A, the array A, the same array we've always worked with. So all you just need to do here is now say eigenvalues, comma, eigenvectors. Since it's eigen now, so it does everything together. And here, you just want to separate. So the eigen of A decomposes the matrix into both eigenvalues and eigenvectors. So you can now extract each one. So in line 7, we're extracting the eigenvalues by calling these eigenvalues with a variable name we have in line 5. And of course, in line 9, we are printing the eigenvectors. So this \n is making sure the eigenvectors go into a new line. So that's another thing we can do to ensure that instead of using the blank print I've always used. So if I run this now, you have the solution. So you have the eigenvalues to be all this. So the eigenvalues are actually complex in this case. So it depends on the kind of matrix you're working with. So in this case, the two of the eigenvalues are complex, but the last one is real because the complex part is actually 0. And of course, looks like so we now have the eigenvectors like that in the next line, right? So made up of both complex and real parts like that. Okay, so that's about eigenvalues and eigenvectors. All right. So we also talk about single value decomposition. In fact, some of these things are actually like the whole idea of machine learning, artificial intelligence, deep learning. So sometimes just look at it like we know we are getting the job done, right? But we don't even really know what is happening in the background. So part of what is happening there is some of those things you're looking at, like single value decomposition. So it constitutes some of the mathematics behind the whole idea of artificial intelligence, under which we have machine learning. So here we have single value decomposition, and it is a factorization of a matrix into 3 matrices. What's the sum called now? The popular name for it is sum. Somehow I don't know the Greek. I mean that sign, and then you have V power H, where U and V are orthogonal matrices. Under matrices, I have a whole video describing different kinds of matrices like idempotent, nilpotent, and things like that. So orthogonal matrices, and this sum symbol is a diagonal matrix containing the singular values. Okay. All right, single value decomposition, SVD, is used in various applications such as data compression, you can see that, noise reduction, and dimensionality reduction in machine learning, as well as in signal processing, image compression, and solving linear inverse problems. Okay, so, and of course, the function is actually SVD. So SVD for single value decomposition inside the LinAlg module and under the line SciPy library. For instance, you want to perform singular value decomposition of a matrix. So the same matrix we've been working with, all you just need to do again is you have A, just get the rows of the matrix, make it into a NumPy array by calling it from a Python list of lists. Okay, and in line 5 now, so the SVD of it gives you those 3 components automatically. So you have the U, you have the sum, that's a summation sign, and then you have the V raised power H, but here we call it VH. And then you can now extract each of them just like we did for eigenvalues and eigenvectors the other time. So all you just need is, I mean, if you have to do this manually, it's going to be a lot of work, right? It's just close to this whole idea of maybe Koleski method and all that. I think we're going to have something close to that after now. So if you just run this, the matrix gets decomposed into those parts. So the matrix U and matrix V are, like we know already, they are orthogonal. They are orthogonal. And then you have the singular values, which are the values you have here. So we have broken down this matrix into this component, and that is actually singular value decomposition. And you have seen its uses, right? This whole image compression and all of these things that happen, it's a whole lot of mathematics, a whole lot of matrix going on in the background. Okay, So how about matrix inversion? Now, sometimes if you want to know if you are told, for instance, if you want to know if a matrix is singular or non-singular, I've told you one of the check is to find if it has a determinant. If it has a determinant, that means it is non-singular. That means it has an inverse. But if the determinant is 0, then that means it is actually singular and you cannot find its inverse. So, of course, we are working with the same matrix we've been working with. So, and we saw that it had a determinant. So it means we can find its inverse for sure. So for matrix inversion, right? I mean, I always have this issue with matrix and matrix. I mean, so so here the function is inv for inversion inside the LinAlg module. Okay. For instance, if you want to invert a matrix, find the inverse of a matrix. For instance, find the inverse of A, the same matrix we've been working with, 3, 1, minus 1, 1, 1, 1, 1, 2, 2, which is derived from the original system of equations we started out with, right? So, and of course, if you need a 2 by 2 matrix and all that, you can always do the same. So again here, now you see, generally, if you're on a more professional note, right? Since if you know you are going to work with this matrix A from the very beginning, once you declare the first time, you don't have to keep repeating it, because once you run it the first time, you can always call it as far as you don't have another matrix A that is overwriting it afterwards. So I mean, but just keep doing this. I mean, for the sake of beginners, so to speak. But it's not necessary. Once you declared it once, even if you have 1,000 cells and you need A in the 900 cell, you just call it out as far as you have run it sometime. That's all you need. So A inverse now, A underscore inv is actually the variable name now, but the actual work is actually being done in this line 5. There's inv bracket A. So that just gives you the inversion straight up, and you get the matrix inverse. The inverse of that matrix. That's how that goes. Okay, so we come again to the idea of LU decomposition. So L, you can take L to be lower and U to be upper, right? So LU decomposition factors a matrix A into the product of a lower triangular matrix L and an upper triangular matrix U. Now, if you still don't understand what the whole idea of, in fact, for you to really have a very nice understanding of this particular video, I think it's all. In fact, I'm going to put the link to the matrix playlist in the description box so you can refer to it in case you don't know, you don't really understand all these lower matrix, upper matrix, singular matrix, and all of these things we've been talking about, right? So LU decomposition factors the matrix into the product of a lower triangular matrix L and an upper triangular matrix U. It is commonly used to solve linear systems of equations efficiently by enabling straightforward and backward substitution. So, in numerical analysis, right, sometimes you want to solve a matrix and it can be quite complicated if you just solve it directly. In fact, in the matrix playlist, there was this time we had to do the Gauss-Seidel method of solution. So, and what we just do is we transform the matrix into a unit matrix, and then that way it's very easy to derive the solutions to the matrix like that. So that is the kind of thing this is helping you with. And there are a few other methods like the Koleski method and all that actually does the same kind of job. So here, the function is the LU function in the LinAlg module, and which is in the SciPy library. And the example is performing LU decomposition of a matrix. For instance, the same matrix, you want to perform the LU decomposition. So you're breaking it, you're separating it into, you're decomposing it into a lower triangular matrix. Of course, the lower triangular matrix, in a lower triangular matrix, right, everything below the principal diagonal that's where you have values, but everything above it is actually 0. For upper triangular matrix, everything below the principal diagonal is actually 0. And you're going to see that with this matrix first hand. Okay. So here you have the same array A, and the actual job is getting done here, LUA, and then you're printing all the PLU, So we have this now. So you have this P, and then you have the lower triangular matrix, and then you have the upper triangular matrix, and that's what you have for the LU decomposition. So you can see this is a lower matrix indeed, because the principal diagonal is like it contains elements 1 1, elements 1 1, 2 2, 3 3. So everything above that you can see is actually 0. Everything below is non-zero. And for the upper triangular matrix, right, everything above the principal diagonal, 1, 1, 2, 2, 3, 3 is actually everything above is non-zero, but everything below is 0. So that's the idea of lower and upper triangular matrices. Okay. And finally, of course, there's a lot more we can do, like the Koleski thing I talked about, So, but these are just some introduction to it. So if you want to learn more, that's why I've made the notes available in the description box. So just get to the link, open the notes, and try different things. Okay. So, and of course, you can try with different matrices, 2 by 2, 4 by 4, 5 by 5, anything. I've used this 3 by 3 matrix because I know it's fairly, it's not too simple and it's not too hard, and then you can work with that. And of course, the advantage of this whole SciPy thing is that, I mean, if you have to find if I was going to do any of the things I've done here manually, maybe I'll still be on the second one by now. But now, because of computation, I'm already on the 7th task like this. So that's one fast advantage of computation. Even if you have to do something manually, this computation can actually help you to get the correct, and it can, with this, you can be assured of what you're doing if your answer is correct or wrong in the long run. You can already do this, get your answer, and then work towards it, like that. So the 7th stuff is to find the exponential and logarithm of a matrix. So, you can actually find the exponent of or logarithm of a matrix. For instance, the functions you need to use in that case will be expm for exponential matrix, and then for log, you use log of a matrix. For instance, I can tell you to evaluate the exponent of matrix A, or the logarithm, natural logarithm of matrix A, given that A is the same matrix we've been working with all this while. All right. So here, in this case, we need to. So don't forget the first thing we've been doing, because for LU decomposition, you have to import it. Don't ever forget that. I've not been emphasizing that a lot. So anything you need to use, if you need to use all of these things, you can just say from SciPy.LinAlg import this, import that. But of course, if you need to, if you don't want to import, right, the other option is to say from you can import SciPy.LinAlg as say SL, and then if you now, okay, maybe I'll just describe that after this last thing I want to do. Okay, so here we have the same matrix. Now the matrix is declared in 3, and A underscore exponent of the matrix, that's what we have there. And log of the matrix, that's also what we have there. So we print them out in lines 9 and 11 now. And I run that. So you have the exponent of the matrix. So what is basically happening here is that, so this is e raised power 3. So exponent, right? This should be like e raised power 3, e raised power 1, e raised power minus 1, and all that. If that is okay, well, I mean, that's how that actually goes. And of course, for the logarithm of A also, so you have all of this happening in the case of a matrix. Now, what I was saying the other time is, if you don't want to keep importing one by one, like, so you have two options, right? You can actually say from SciPy.LinAlg import all these things, or you can say that you can actually say import SciPy dot LinAlg as say SL. You can do that, so that if you now have, let's make use of another matrix. Let's call it probably matrix B. Let's say we have a matrix B. So this is, let's now say this is 3, 1, 3, 1, 1, 2, 3, 1, 1, 2. Okay. And then probably we need to do whatever. Let's say we now need to do, say, okay, let's do different things with this actually. Of course, if we print this, print A, you get, you can already have that printed. So it's a 2 by 3, I mean a 2 by 2 matrix. Of course, the determinant of that will be 6 minus 1, that's 5. So let's say we want to do the determinant. So let's say we want to do that A, right? So we just say that A. Now, where the actual work is, so that's this. So for you to get this det, now you have to call it from SL, because it's inside SciPy.LinAlg. So you now say SL dot det, and then you have, okay, let's call this B, since we've always used B. So we now say SL.B. So it means that from inside SciPy.LinAlg, we are calling the det function. So we want to find the determinant of that, which you know is already 3 times 2, 6 minus 1, 5. So that is 5 like that. Okay, I've not said to print that. So print that A, and that is 5, as expected. Okay, so let's say, okay, let me call it det B, right? Det B. So if you don't want to keep calling those, so it means you need to know, as far as you master all the functions in your head, or I mean, you can always refer to them online or something. You can always do that. Okay, let's say now we want to find, what else did we find the other time? You want to find the inverse, right? So let's say we just copy this. So I don't have to declare the B again because it's already been declared up here. So maybe I need the inverse of B. So that's inv B. I just say SL, and we know the function for that is INV. So I just say print INV B. So that gives us the inverse like that. So that's the inverse of B. So let's say again, what else did we do? Say we want to solve the system. Okay. 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 I mean, maybe I can leave that. So let's just do something we can do straight up. What else can we do? So we need the exponent, or let's do the LU decomposition. Let's say we do LU decomposition of B. So we have LUB. So again, we say SL dot LU because LU comes from that, and then we have LUB like this, and then that gives us all of that decomposition that way. All right, so let's stop there. You can always try your hands on the other things like that. So thanks for listening thus far. If you have not subscribed, be sure to do that. Hit the notification bell so you can always get alerted anytime a new video is released. Then of course, comment, talk about what you like to learn, talk about if you need clarification on something, then like and share as you look up to the next video. See you then.